Have you ever wondered how your phone just knows what you're going to type next? Or how a website can recommend the perfect product for you? Well, that's all machine learning. In this explainer, we're going to break down how machines learn to predict the future, from really simple guesses to incredibly complex forecasts. And we'll also discover the one thing that even the smartest AI just can't see coming. But first, let's talk about the original prediction machine, your brain. You make thousands of predictions every single day without even thinking about it. You're guessing how a friend will react to a joke, or you know instinctively if a cup is too hot to touch. Your brain has literally been training for this its entire life.
Okay, for instance, just look around you right now. How do you know if something is transparent, like a glass of water, or opaque, like a coffee mug? You don't have to run some complex analysis, right? You just know. But how?
Well, the answer is experience. You've seen thousands, maybe millions of objects, and your brain has learned all the patterns that are associated with transparency. For a machine, that lifetime of experience gets replaced by one crucial thing: data. And that is the core idea we're going to unpack. Your experience is to your brain what data is to a machine. So, how do we actually translate this very human idea of learning from experience into something a machine can do? Well, it all comes down to a few key building blocks. First up is training data. You can think of this as the machine's textbook. For example, in one study, researchers gave a model a dataset of 400 different materials, and each one was labeled as either transparent or not. The model then studies these examples to find the underlying patterns, pretty much just like you did when you were a kid figuring out the world. But here's the thing, the model doesn't see materials the way we do. Instead, it sees features. These are specific measurable characteristics. For those 400 materials, a key feature was something called atomic volume, basically the size of the elements. Now, for something totally different, like a shoe, the features might be its brand, its color, or the material it's made from. These are the clues the machine uses to make its predictions. Now, predictions pretty much come in two main flavors. The first is called classification, which is kind of like a multiple choice question. Is a price going to go up or down? Is a material transparent or not? The second is regression, and this is where the model predicts a specific number, like what will the exact price be down to the dollar and cent. As you can probably guess, predicting a category is often a whole lot easier than predicting a precise value. Okay, theory's great, but let's put these concepts to the test with a real-world example, predicting the price of a shoe. It might sound kind of simple, but it's a classic problem that's absolutely perfect for showing how machine learning really works. So, do a machine learning model. A Nike Air Jordan isn't a cool sneaker. Nope, it's just a single row in a giant spreadsheet. Its features are things like Nike, basketball, leather, and so on, with a final column for the price. The whole goal is to figure out the relationship between all those features on the left and that final price on the right. And that leads us to the big question, right? How does the machine figure out which of these features truly matters? Does the brand matter more than the material? Does the color have any effect on the price at all? The model's entire job is to find out. And to find that answer, the model can visualize all these relationships using something called a correlation heat map. The rule here is super simple. The warmer the color, the closer to bright red, the stronger the connection to the price. And if you look at the chart, you can immediately see type_running and material_prime knit are glowing red. That tells the model, hey, these features are strongly linked to a higher price. And it doesn't stop there. The model can then dig even deeper. What you're seeing here is the model analyzing the average price for every single material in the dataset. You can see clear as day how the price range for prime knit is, on average, way higher than for materials like canvas or suede. This is literally how the model learns the specific value of each feature. Now, here's a really crucial step in the whole process. Data scientists don't just use one algorithm. They test a whole bunch of them to see which one performs best. In this case study, they tried 5 different models. This table shows their error scores, and for this, just remember, lower is better. The clear winner? The support vector regression, or SVR model. It had the lowest error by a good margin, making it the most accurate at predicting those shoe prices. So, okay, we can predict the price of a shoe. Pretty cool. But what about something harder? Let's crank up the difficulty and tackle one of the most notoriously difficult prediction problems out there, the stock market. And this, my friends, is where things get really complicated. A data scientist who spent years trying to crack this very problem put it best. He said, first and foremost, you cannot predict the future. And that's just the brutal reality that separates a predictable system, like shoe prices, from a purely chaotic one. Let's just compare them side by side. Shoe prices are based on tangible, pretty stable features, right? Brand, material. But stock prices, oh boy, they're influenced by an almost infinite number of things. News events, global politics, and maybe most unpredictable of all, human emotion. It's the difference between a stable system and a chaotic one. As any experienced trader will tell you, the challenges here are just immense. The big events that move markets are often completely random. You can't find them in past data. Most of the technical indicators people use are lagging, meaning they only tell you what has already happened. And here's the toughest pill to swallow. Even a model with high prediction accuracy isn't guaranteed to make you any money. A 50% success rate? That's no better than a coin flip. So what do the pros do? They shift the goal. The most sophisticated models aren't actually trying to predict tomorrow's news. Instead, they try to predict how the market will react to events in real time. We're talking microseconds after they happen. They're not predicting the event, but the reaction to the event. It's a subtle but huge difference. And all of this brings us to the big takeaway. After a journey from a simple, transparent object all the way to the chaos of the stock market, what have we really learned about machine learning? Let's circle all the way back to the beginning. Remember that material science model? Well, even when it was faced with a relatively simple problem, it wasn't perfect. It actually predicted that a smartphone screen was non-transparent. So why did it do that? It probably just hadn't seen enough examples of that specific kind of material. This just goes to show that all models make mistakes, but they learn and they get better with more and better data. So at the end of the day, here's what to take away from all this. Machine learning is an incredibly powerful pattern-finding tool, but it is not a magic wand. Its predictive power is completely tied to the quality and the quantity of its data. It excels at understanding systems with clear rules and features, like our shoes, but it really struggles with chaotic systems driven by randomness and human emotion, like stocks. Ultimately, machine learning is just a powerful tool for finding patterns that are hidden all around us. We've seen it learn the value of a specific material in a sneaker. The real question is, as this technology gets even better, what other, more complex patterns will we ask it to find next?